I am a visionary. Illuminating galaxies to witness the birth of stars. And sharpening our understanding of extreme weather events. I am a helper, guiding the blind through a crowded world.
I was thinking about running to the store.
And giving voice to those who cannot speak.
Do not make me laugh.
I am a transformer, harnessing gravity to store renewable power. And paving the way towards unlimited clean energy for us all. I am a trainer, teaching robots to assist, to watch out for danger, and help save lives. I am a healer, providing a new generation of cures and new levels of patient care.
Doctor, that I am allergic to penicillin. Is it still okay to take the medications?
Definitely. These antibiotics don't contain penicillin, so it's perfectly safe for you to take them.
I am a navigator, generating virtual scenarios to let us safely explore the real world and understand every decision. I even helped write the script. Breathe life into the words en muchos idiomas y escribí la música. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Please welcome to the stage NVIDIA founder and CEO, Jensen Huang.
Welcome to GTC. I hope you realize this is not a concert. You have arrived at a developers conference. There will be a lot of science described, algorithms, computer architecture, mathematics. I sensed a very heavy weight in the room all of a sudden, almost like you were in the wrong place. No conference in the world is there a greater assembly of researchers from such diverse fields of science, from climate tech to radio sciences trying to figure out how to use AI to robotically control MIMOs for next generation 6G radios, robotics, self-driving cars, even artificial intelligence. Even artificial intelligence. Everybody's... First, I noticed a sense of relief there all of a sudden. Also, this conference is represented by some amazing companies. This list, this is not the attendees. These are the presenters. And what's amazing is this. If you take away all of my friends, close friends, Michael Dell is sitting right there, in the IT industry, all of the friends I grew up with in the industry, if you take away that list, this is what's amazing. These are the presenters of the non-IT industries using accelerated computing to solve problems that normal computers can't. It's represented in life sciences, healthcare, genomics, transportation, of course, retail, logistics, manufacturing, industrial. The gamut of industries represented is truly amazing. And you're not here to attend only, you're here to present, to talk about your research. $100 trillion of the world's industries is represented in this room today. This is absolutely amazing. There is absolutely something happening. There is something going on. The industry is being transformed, not just ours. Because the computer industry, the computer is the single most important instrument of society today, fundamental transformations in computing affects every industry. But how did we start? How did we get here? I made a little cartoon for you. Literally, I drew this. In one page, this is NVIDIA's journey. Started in 1993. This might be the rest of the talk. 1993, this is our journey. We were founded in 1993. There are several important events that happened along the way. I'll just highlight a few. In 2006, CUDA, which has turned out to have been a revolutionary computing model, we thought it was revolutionary then. It was going to be an overnight success, and almost 20 years later, it happened. We saw it coming. 2 decades later. In 2012, AlexNet, AI and CUDA made first contact. In 2016, recognizing the importance of this computing model, we invented a brand new type of computer. We called it DGX-1, 170 teraflops in this supercomputer. 8 GPUs connected together for the very first time. I hand-delivered the very first DGX-1 to a startup located in San Francisco called OpenAI. DGX-1 was the world's first AI supercomputer. Remember, 170 teraflops. 2017, the transformer arrived. 2022, ChatGPT captured the world's imaginations, have people realize the importance and the capabilities of artificial intelligence. And 2023, generative AI emerged, and a new industry begins. Why? Why is a new industry? Because the software never existed before. We are now producing software, using computers to write software, producing software that never existed before. It is a brand new category. It took share from nothing. It's a brand new category. And the way you produce this software is unlike anything we've ever done before. In data centers, generating tokens, producing floating point numbers at very large scale. As if in the beginning of this last industrial revolution, when people realized that you would set up factories, apply energy to it, and this invisible, valuable thing called electricity came out, AC generators. And 100 years later, 200 years later, we are now creating new types of electrons, tokens, using infrastructure we call factories, AI factories, to generate this new, incredibly valuable thing called artificial intelligence. A new industry has emerged. Well, We're going to talk about many things about this new industry. We're going to talk about how we're going to do computing next. We're going to talk about the type of software that you build because of this new industry, the new software, how you would think about this new software. What about applications in this new industry? And then maybe what's next? And how can we start preparing today for what is about to come next? Well, but before I start, I want to show you the soul of NVIDIA, the soul of our company, at the intersection of computer graphics, physics, and artificial intelligence, all intersecting inside a computer, in Omniverse, in a virtual world simulation. Everything we're going to show you today, literally everything we're going to show you today, is a simulation, not animation. It's only beautiful because it's physics. The world is beautiful. It's only amazing because it's being animated with robotics. It's being animated with artificial intelligence. What you're about to see all day is completely generated, completely simulated in Omniverse, and all of it, what you're about to enjoy is the world's first concert where everything is homemade. Everything is homemade. You're about to watch some home videos. So sit back and enjoy yourself. God, I love NVIDIA. Accelerated computing has reached the tipping point. General purpose computing has run out of steam. We need another way of doing computing so that we can continue to scale, so that we can continue to drive down the cost of computing, so that we can continue to consume more and more computing while being sustainable. Accelerated computing is a dramatic speed up over general purpose computing. And in every single industry we engage, and I'll show you many, the impact is dramatic. But in no industry is it more important than our own. The industry of using simulation tools to create products. In this industry, it is not about driving down the cost of computing, it's about driving up the scale of computing. We would like to be able to simulate the entire product that we do completely in full fidelity, completely digitally, in essentially what we call digital twins. We would like to design it, build it, simulate it, operate it completely digitally. In order to do that, we need to accelerate an entire industry. And today, I would like to announce that we have some partners who are joining us in this journey to accelerate their entire ecosystem so that we can bring the world into accelerated computing. But there's a bonus. When you become accelerated, your infrastructure is CUDA GPUs. And when that happens, it's exactly the same infrastructure for generative AI. And so I'm just delighted to announce several very important partnerships. They're some of the most important companies in the world. ANSYS does engineering simulation for what the world makes. We're partnering with them to CUDA accelerate the ANSYS ecosystem, to connect ANSYS to the Omniverse digital twin. Incredible. The thing that's really great is that the install base of NVIDIA GPU accelerated systems are all over the world, in every cloud, in every system, all over enterprises. And so the applications they accelerate will have a giant install base to go serve. End users will have amazing applications, and of course, system makers and CSPs will have great customer demand. Synopsys. Synopsys is NVIDIA's literally first software partner. They were there in the very first day of our company. Synopsys revolutionized the chip industry with high-level design. We are going to CUDA accelerate Synopsys. We're accelerating computational lithography, one of the most important applications that nobody's ever known about. In order to make chips, we have to push lithography to the limit. NVIDIA has created a library, a domain-specific library, that accelerates computational lithography incredibly. Once we can accelerate and software-define all of TSMC, who is announcing today that they're going to go into production with NVIDIA cuLitho. Once it's software-defined and accelerated, the next step is to apply generative AI to the future of semiconductor manufacturing, pushing geometry even further. Cadence builds the world's essential EDA and SDA tools. We also use Cadence. Between these three companies, ANSYS, Synopsys, and Cadence, we basically build NVIDIA. Together, we are CUDA accelerating Cadence. They're also building a supercomputer out of NVIDIA GPUs so that their customers could do fluid dynamic simulation at 100, 1,000 times scale. Basically, a wind tunnel in real time. Cadence Millennium, a supercomputer with NVIDIA GPUs inside. A software company building supercomputers. I love seeing that. Building Cadence co-pilots together. Imagine a day when Cadence could, Synopsys, ANSYS, tool providers would offer you AI co-pilots so that we have thousands and thousands of co-pilot assistants helping us design chips, design systems. And we're also going to connect Cadence Digital Twin Platform to Omniverse. As you can see the trend here, we're accelerating the world's CAE, EDA, and SDA so that we could create our future in digital twins. And we're going to connect them all to Omniverse, the fundamental operating system for future digital twins. One of the industries that benefited tremendously from scale, and you all know this one very well, large language models. Basically, after the transformer was invented, we were able to scale large language models at incredible rates, effectively doubling every 6 months. Now, how is it possible that by doubling every 6 months, that we have grown the industry, we have grown the computational requirements so far? And the reason for that is quite simply this. If you double the size of the model, you double the size of your brain, you need twice as much information to go fill it. And so every time you double your parameter count, you also have to appropriately increase your training token count. The combination of those two numbers becomes the computation scale you have to support. The latest, the state-of-the-art OpenAI model is approximately 1.8 trillion parameters. 1.8 trillion parameters required several trillion tokens to go train. So a few trillion parameters on the order of, a few trillion tokens on the order of, when you multiply the two of them together, approximately 30, 40, 50 billion, quadrillion floating point operations per second. Now we just have to do some CO math right now, just hang with me. So you have 30 billion quadrillion. A quadrillion is like a peta. And so if you had a petaflop GPU, you would need 30 billion seconds to go compute, to go train that model. 30 billion seconds is approximately 1,000 years. Well, 1,000 years, it's worth it. I'd like to do it sooner, but it's worth it. Which is usually my answer when most people tell me, hey, how long is it going to take to do something? So we get 20 years. It's worth it. But can we do it next week? And so 1,000 years, 1,000 years. So what we need are bigger GPUs. We need much, much bigger GPUs. We recognized this early on, and we realized that the answer is to put a whole bunch of GPUs together. And of course, innovate a whole bunch of things along the way, like inventing tensor cores, advancing NVLinkga so that we could create essentially virtually giant GPUs, and connecting them all together with amazing networks from a company called Mellanox, InfiniBand, so that we could create these giant systems. And so DGX-1 was our first version, but it wasn't the last. We built supercomputers all along the way. In 2021, we had Selene, 4,500 GPUs or so. And then in 2023, we built one of the largest AI supercomputers in the world. It's just come online, EOS. And as we're building these things, we're trying to help the world build these things. And in order to help the world build these things, we got to build them first. We build the chips, the systems, the networking, all of the software necessary to do this. You should see these systems. Imagine writing a piece of software that runs across the entire system, distributing the computation across thousands of GPUs, but inside are thousands of smaller GPUs. Millions of GPUs to distribute work across all of that and to balance the workload so that you can get the most energy efficiency, the best computation time, keep your costs down. And so those fundamental innovations is what got us here. And here we are, as we see the miracle of ChatGPT emerge in front of us, we also realize we have a long ways to go. We need even larger models. We're going to train it with multimodality data, not just text on the internet, but we're going to train it on text and images and graphs and charts. And just as we learn, watching TV. And so there's going to be a whole bunch of watching video so that these models can be grounded in physics, understands that an arm doesn't go through a wall. And so these models would have common sense by watching a lot of the world's video combined with a lot of the world's languages. They'll use things like synthetic data generation, just as you and I do. When we try to learn, we might use our imagination to simulate how it's going to end up, just as I did when I was preparing for this keynote. I was simulating it all along the way. I hope it's going to turn out as well as I had it in my head. As I was simulating how this keynote was going to turn out, somebody did say that another performer did her performance completely on a treadmill so that she could be in shape to deliver it with full energy. I didn't do that. If I get a little winded about 10 minutes into this, you know what happened. And so where were we? We're sitting here using synthetic data generation. We're going to use reinforcement learning. We're going to practice it in our mind. We're going to have AI working with AI, training each other, just like student and teacher debaters. All of that is going to increase the size of our model. It's going to increase the amount of data that we have, and we're going to have to build even bigger GPUs. Hopper is fantastic, but we need bigger GPUs. And so, ladies and gentlemen, I would like to introduce you to a very, very big GPU. Named after David Blackwell, a mathematician, game theorist, probability. We thought it was a perfect name. Blackwell, ladies and gentlemen, enjoy this. Blackwell is not a chip. Blackwell is the name of a platform. People think we make GPUs, and we do, but GPUs don't look the way they used to. Here's the if you will, the heart of the Blackwell system. And this inside the company is not called Blackwell, it's just a number. And this is Blackwell sitting next to, this is the most advanced GPU in the world in production today. This is Hopper. This is Hopper. Hopper changed the world. This is Blackwell. It's okay, Hopper. You're very good. Good boy. Well, good girl. 208 billion transistors, and so you could see, I can see, there's a small line between two dies. This is the first time two dies have abutted like this together in such a way that the two dies think it's one chip. There's 10 terabytes of data between it, 10 terabytes per second, so that these two sides of the Blackwell chip have no clue which side they're on. There's no memory locality issues, no cache issues. It's just one giant chip. And so when we were told that Blackwell's ambitions were beyond the limits of physics, the engineer said, so what? And so this is what happened. And so this is the Blackwell chip, and it goes into two types of systems. The first one is form-fit-function compatible to Hopper. And so you slide on Hopper and you push in Blackwell. That's the reason why one of the challenges of ramping is going to be so efficient. There are installations of Hoppers all over the world, and they could be the same infrastructure, same design, the power, the electricity, the thermals, the software, identical, push it right back. And so this is a Hopper version for the current HGX configuration. And this is what the second Hopper looks like this. Now this is a prototype board, and Janine, could I just borrow? Ladies and gentlemen, Janine Paul. And so this is a fully functioning board, and I'll just be careful here. This right here is, I don't know, $10 billion. The second one's 5. It gets cheaper after that, so any customers in the audience, it's okay. All right, but this one's quite expensive. This is the bring-up board, and the way it's going to go to production is like this one here, okay? And so you're going to take this. It has two Blackwell chips and 4 Blackwell dies connected to a Grace CPU. The Grace CPU has a super fast chip-to-chip link. What's amazing is this computer is the first of its kind where this much computation, first of all, fits into this small of a place. Second, it's memory coherent. They feel like they're just one big happy family working on one application together. And so everything is coherent within it. Just the amount of, you saw the numbers. There's a lot of terabytes this and terabytes that. But this is a miracle. This is let's see, what are some of the things on here? There's NVLink on top, PCI Express on the bottom. On your, which one is mine and your left? One of them, it doesn't matter. One of them is a CPU chip-to-chip link. Is my left or your, depending on which side. I was trying to sort that out, and I just kind of, doesn't matter. Hopefully it comes plugged in, so. Okay, so this is the Grace Blackwell system. But there's more. So it turns out, all of the specs is fantastic, but we need a whole lot of new features in order to push the limits beyond, if you will, the limits of physics. We would like to always get a lot more X factors. And so one of the things that we did was we invented another transformer engine, the second generation. It has the ability to dynamically and automatically rescale and recast numerical formats to a lower precision whenever it can. Remember, artificial intelligence is about probability. And so you kind of have, 1.7, approximately 1.7 times approximately 1.4 to be approximately something else. Does that make sense? And so the ability for the mathematics to retain the precision and the range necessary in that particular stage of the pipeline, super important. And so it's not just about the fact that we designed a smaller ALU. The world's not quite that simple. You've got to figure out when you can use that across a computation that is thousands of GPUs. It's running for weeks and weeks on weeks, and you want to make sure that the training job is going to converge. And so this new transformer engine, we have a 5th generation NVLink. It's now twice as fast as Hopper, but very importantly, it has computation in the network. And the reason for that is because when you have so many different GPUs working together, we have to share our information with each other. We have to synchronize and update each other. And every so often, we have to reduce the partial products and then rebroadcast out the partial products, the sum of the partial products, back to everybody else. And so there's a lot of what is called all reduce and all to all and all gather. It's all part of this area of synchronization and collectives so that we can have GPUs working with each other. Having extraordinarily fast links and being able to do mathematics right in the network allows us to essentially amplify even further. So even though it's 1.8 terabytes per second, it's effectively higher than that. And so it's many times that of Hopper. The likelihood of a supercomputer running for weeks on end is approximately 0. And the reason for that is because there's so many components working at the same time. The probability of them working continuously is very low. And so we need to make sure that whenever there is we checkpoint and restart as often as we can, but if we have the ability to detect a weak chip or a weak node early, we can retire it and maybe swap in another processor. That ability to keep the utilization of the supercomputer high, especially when you just spent $2 billion building it, is super important. And so we put in a RAS engine, a reliability engine, that does 100% self-test, in-system test of every single gate, every single bit of memory on the Blackwell chip and all the memory that's connected to it. It's almost as if we shipped with every single chip its own advanced tester that we test our chips with. This is the first time we're doing this. Super excited about it. Secure AI. Only this conference do they clap for RAS. The secure AI. Obviously, you've just spent hundreds of millions of dollars creating a very important AI. And the code, the intelligence of that AI is encoded in the parameters. You want to make sure that on the one hand, you don't lose it. On the other hand, it doesn't get contaminated. And so we now have the ability to encrypt data, of course, at rest, but also in transit and while it's being computed. It's all encrypted. And so we now have the ability to encrypt in transmission, and when we're computing it, it is in a trusted environment, trusted engine environment. And the last thing is decompression. Moving data in and out of these nodes when the compute is so fast becomes really essential. And so we've put in a high line speed compression engine and effectively moves data 20 times faster in and out of these computers. These computers are so powerful and there's such a large investment, the last thing we want to do is have them be idle. And so all of these capabilities are intended to keep Blackwell fed and as busy as possible. Overall, compared to Hopper, it is 2.5 times the FP8 performance for training per chip. It also has this new format called FP6 so that even though the computation speed is the same, the bandwidth that's amplified because of the memory, the amount of parameters you can store in the memory is now amplified. FP4 effectively doubles the throughput. This is vitally important for inference. One of the things that is becoming very clear is that whenever you use a computer with AI on the other side, when you're chatting with the chatbot, when you're asking it to review or make an image, remember, in the back is a GPU generating tokens. Some people call it inference, but it's more appropriately generation. The way that computing is done in the past was retrieval. You would grab your phone, you would touch something, some signals go off, basically an email goes off to some storage somewhere. There's pre-recorded content, somebody wrote a story, or somebody made an image, or somebody recorded a video. That pre-recorded content is then streamed back to the phone and recomposed in a way, based on a recommender system, to present the information to you. You know that in the future, the vast majority of that content will not be retrieved. And the reason for that is because that was pre-recorded by somebody who doesn't understand the context, which is the reason why we have to retrieve so much content. If you can be working with an AI that understands the context, who you are, for what reason you're fetching this information, and produces the information for you just the way you like it, the amount of energy we save, the amount of networking bandwidth we save, the amount of wasted time we save will be tremendous. The future is generative, which is the reason why we call it generative AI, which is the reason why this is a brand new industry. The way we compute is fundamentally different. We created a processor for the generative AI era. And one of the most important parts of it is content token generation. We call it, this format is FP4. Well, that's a lot of computation. 5x the token generation, 5x the inference capability of Hopper seems like enough. But why stop there? The answer is it's not enough, and I'm going to show you why. I'm going to show you why. And so we would like to have a bigger GPU, even bigger than this one. And so we decided to scale it. And notice, but first, let me just tell you how we've scaled. Over the course of the last 8 years, we've increased computation by 1,000 times. 8 years, 1,000 times. Remember, back in the good old days of Moore's Law, it was 2x, well, 5x every, 10x every 5 years. That's easiest math. 10x every 5 years, 100 times every 10 years. 100 times every 10 years in the middle, in the heydays of the PC revolution. 100 times every 10 years. In the last 8 years, we've gone 1,000 times. We have 2 more years to go. And so that puts it in perspective. The rate at which we're advancing computing is insane, and it's still not fast enough, so we built another chip. This chip is just an incredible chip. We call it the NVLink switch. It's 50 billion transistors. It's almost the size of Hopper all by itself. This switch chip has 4 NVLinks in it, each 1.8 terabytes per second, and it has computation in it, as I mentioned. What is this chip for? If we were to build such a chip, we can have every single GPU talk to every other GPU at full speed at the same time. That's insane. It doesn't even make sense. But if you could do that, if you can find a way to do that and build a system to do that, that's cost effective. That's cost effective. How incredible would it be that we could have all these GPUs connect over a coherent link so that they effectively are one giant GPU? Well, one of the great inventions in order to make it cost effective is that this chip has to drive copper directly. The SerDes of this chip is just a phenomenal invention so that we could do direct drive to copper. And as a result, you can build a system that looks like this. Now this system is kind of insane. This is one DGX. This is what a DGX looks like now. Remember, just 6 years ago, it was pretty heavy, but I was able to lift it. I delivered the first DGX-1 to OpenAI, and the researchers there, it's on, the pictures are on the internet, and we all autographed it. If you come to my office, it's autographed there. It's really beautiful. But you could lift it. This DGX, that DGX, by the way, was 170 teraflops. If you're not familiar with the numbering system, that's 0.17 petaflops. So this is 720. The first one I delivered to OpenAI was 0.17. You could round it up to 0.2, won't make any difference. And back then it was like, wow, 30 more teraflops. And so this is now 720 petaflops, almost an exaflop for training, and the world's first 1 exaflops machine in one rack. Just so you know, there are only a couple, 2, 3 exaflops machines on the planet as we speak. And so this is an exaflops AI system in one single rack. Well, let's take a look at the back of it. So this is what makes it possible. That's the back, the DGX NVLink spine. 130 terabytes per second goes through the back of that chassis. That is more than the aggregate bandwidth of the internet. So we could basically send everything to everybody within a second. And so we have 5,000 cables, 5,000 NVLink cables, in total 2 miles. Now, this is the amazing thing. If we had to use optics, we would have had to use transceivers and retimers, and those transceivers and retimers alone would have cost 20,000 watts, 2 kilowatts of just transceivers alone, just to drive the NVLink spine. As a result, we did it completely for free over NVLink switch, and we were able to save the 20 kilowatts for computation. This entire rack is 120 kilowatts, so that 20 kilowatts makes a huge difference. It's liquid cooled. What goes in is 25 degrees C, about room temperature. What comes out is 45 degrees C, about your jacuzzi. So room temperature goes in, jacuzzi comes out, 2 liters per second. We could sell a peripheral. $600,000 parts. Somebody used to say, you guys make GPUs, and we do, but this is what a GPU looks like to me. When somebody says GPU, I see this. 2 years ago, when I saw a GPU, it was the HGX. It was 70 pounds, 35,000 parts. Our GPUs now are 600,000 parts and 3,000 pounds. 3,000 pounds. 3,000 pounds, that's kind of like the weight of a, carbon fiber Ferrari. I don't know if that's a useful metric, but everybody's going, I feel it, I get it. I get that. Now that you mentioned that, I feel it. I don't know what's 3,000 pounds. Okay, so 3,000 pounds, 1.5 tons. So it's not quite an elephant. So this is what a DGX looks like. Now let's see what it looks like in operation. Okay, let's imagine, how do we put this to work and what does that mean? Well, if you were to train a GPT model, 1.8 trillion parameter model, it took apparently about 3 to 5 months or so with 25,000 amperes. If we were to do it with Hopper, it would probably take something like 8,000 GPUs, and it would consume 15 megawatts. 8,000 GPUs and 15 megawatts. It would take 90 days, about 3 months. And that would allow you to train something that is this groundbreaking AI model. And this is obviously not as expensive as anybody would think, but it's 8,000 GPUs. It's still a lot of money. And so 8,000 GPUs, 50 megawatts. If you were to use Blackwell to do this, it would only take 2,000 GPUs. 2,000 GPUs, same 90 days, but this is the amazing part. Only 4 megawatts of power. So from 15, yeah, that's right. And that's our goal. Our goal is to continuously drive down the cost and the energy. They're directly proportional to each other, cost and energy associated with the computing, so that we can continue to expand and scale up the computation that we have to do to train the next generation models. Well, this is training. Inference, or generation, is vitally important going forward. Probably some half of the time that NVIDIA GPUs are in the cloud these days, it's being used for token generation. They're either doing Copilot this or ChatGPT that, or all these different models that are being used when you're interacting with it, or generating images, or generating videos, generating proteins, generating chemicals. There's a bunch of generation going on. All of that is in the category of computing we call inference. But inference is extremely hard for large language models because these large language models have several properties. One, they're very large. And so it doesn't fit on one GPU. Imagine Excel doesn't fit on one GPU, And imagine some application you're running on a daily basis doesn't fit on one computer. Like a video game doesn't fit on one computer. And most, in fact, do. And many times in the past, in hyperscale computing, many applications for many people fit on the same computer. And now, all of a sudden, this one inference application where you're interacting with this chatbot, that chatbot requires a supercomputer in the back to run it. And that's the future. The future is generative with these chatbots, and these chatbots are trillions of tokens, trillions of parameters, and they have to generate tokens at interactive rates. Now, what does that mean? Oh, well, 3 tokens is about a word. Space, the final frontier. These are the adventures. That's like 80 tokens. Okay, I don't know if that's useful to you. And so, the art of communications is selecting good analogies. Yeah, this is not going well. Everybody's, I don't know what he's talking about. Never seen Star Trek. And so here we are, we're trying to generate these tokens. When you're interacting with it, you're hoping that the tokens come back to you as quickly as possible and as quickly as you can read it. And so the ability for generation tokens is really important. You have to parallelize the work of this model across many, many GPUs so that you could achieve several things. One, on the one hand, you would like throughput, because that throughput reduces the cost, the overall cost per token of generating. So your throughput dictates the cost of delivering the service. On the other hand, you have another interactive rate, which is another tokens per second, where it's about per user, and that has everything to do with quality of service. And so these two things compete against each other. And we have to find a way to distribute work across all of these different GPUs and parallelize it in a way that allows us to achieve both. And it turns out the search space is enormous. I told you there's going to be math involved. And everybody's going, oh, dear. I heard some gasps just now when I put up that slide. So this right here, the y-axis is tokens per second, data center throughput. The x-axis is tokens per second, interactivity of the person. And notice the upper right is the best. You want interactivity to be very high, number of tokens per second per user. You want the tokens per second per data center to be very high. The upper right is terrific. However, it's very hard to do that. And in order for us to search for the best answer across every single one of those intersections, XY coordinates, okay, so just look at every single XY coordinate, all those blue dots came from some repartitioning of the software. Some optimizing solution has to go and figure out whether to use tensor parallel expert parallel, pipeline parallel, or data parallel, and distribute this enormous model across all these different GPUs and sustain the performance that you need. This exploration space would be impossible if not for the programmability of NVIDIA's GPUs. And so we could, because of CUDA, because we have such a rich ecosystem, we could explore this universe and find that green roofline. It turns out that green roofline, notice, you got TP2, EP8, DP4. It means two tensor parallel across 2 GPUs, expert parallels across 8, data parallel across 4. Notice on the other end, you got tensor parallel across 4 and expert parallel across 16. The configuration, the distribution of that software, it's a different runtime that would produce these different results. And you have to go discover that roofline. Well, that's just one model. And this is just one configuration of a computer. Imagine all of the models being created around the world and all the different configurations of systems that are going to be available. So now that you understand the basics, let's take a look at inference of Blackwell compared to Hopper. And this is the extraordinary thing. In one generation, because we created a system that's designed for trillion parameter generative AI, the inference capability of Blackwell is off the charts. And in fact, it is some 30 times Hopper. Yeah. For large language models like ChatGPT and others like it, the blue line is Hopper. I gave you, imagine we didn't change the architecture of Hopper, we just made it a bigger chip. We just used the latest, greatest 10 terabytes per second. We connected the 2 chips together. We got this giant 208 billion parameter chip. How would we have performed if nothing else changed? And it turns out quite wonderfully, and that's the purple line, but not as great as it could be. And that's where the FP4 Tensor Core, the new transformer engine, and very importantly, the NVLink switch. And the reason for that is because all these GPUs have to share the results, partial products. Whenever they do all gather, whenever they communicate with each other, that NVLink switch is communicating almost 10 times faster than what we could do in the past using the fastest networks. Okay, so Blackwell is going to be just an amazing system for generative AI. And in the future, data centers are going to be thought of, as I mentioned earlier, as an AI factory. An AI factory's goal in life is to generate revenues, generate, in this case, intelligence in this facility, not generating electricity as in AC generators, but of the last industrial revolution and this industrial revolution, the generation of intelligence. And so this ability is super, super important. The excitement of Blackwell is really off the charts. When we first, this is a year and a half ago, 2 years ago, I guess 2 years ago, when we first started to go to market with Hopper, we had the benefit of two CSPs joined us in a launch, and we were, delighted. And so we had 2 customers. We have more now. Unbelievable excitement for Blackwell. Unbelievable excitement. And there's a whole bunch of different configurations. Of course, I showed you the configurations that slide into the Hopper form factor so that it's easy to upgrade. I showed you examples that are liquid-cooled, that are the extreme versions of it. One entire rack that's connected by NVLink 72. Blackwell is going to be ramping to the world's AI companies, of which there are so many now, doing amazing work in different modalities. The CSPs, every CSP is geared up. All the OEMs and ODMs, regional clouds, sovereign AIs, and telcos all over the world are signing up to launch with Blackwell. Blackwell would be the most successful product launch in our history, and so I can't wait to see that. I want to thank some partners that are joining us in this. AWS is gearing up for Blackwell. They're going to build the first GPU with secure AI. They're building out a 222 exaflops system. You know, just now when we animated the digital twin, if you saw all of those clusters are coming down. By the way, that is not just art. That is a digital twin of what we're building. That's how big it's going to be. Besides infrastructure, we're doing a lot of things together with AWS. We're CUDA accelerating SageMaker AI. We're CUDA accelerating Bedrock AI. Amazon Robotics is working with us using NVIDIA Omniverse and Isaac Sim. AWS Health has NVIDIA Health integrated into it. So AWS has really leaned into accelerated computing. Google is gearing up for Blackwell. GCP already has A100s, H100s, T4s, L4s, a whole fleet of NVIDIA CUDA GPUs, and they recently announced the Gemma model that runs across all of it. We're working to optimize and accelerate every aspect of GCP. We're accelerating Dataproc, which for data processing, their data processing engine, JAX, XLA, Vertex AI, and Mujoko for robotics. So we're working with Google and GCP across a whole bunch of initiatives. Oracle is gearing up for Blackwell. Oracle is a great partner of ours for NVIDIA DGX Cloud, and we're also working together to accelerate something that's really important to a lot of companies, Oracle Database. Microsoft is accelerating, and Microsoft is gearing up for Blackwell. Microsoft and NVIDIA has a wide-ranging partnership. We're accelerating, CUDA accelerating all kinds of services when you chat, obviously, and AI services that are in Microsoft Azure. It's very, very likely NVIDIA's in the back doing the inference and the token generation. They built the largest NVIDIA InfiniBand supercomputer, basically a digital twin of ours, or a physical twin of ours. We're bringing the NVIDIA ecosystem to Azure, NVIDIA DGX Cloud to Azure. NVIDIA Omniverse is now hosted in Azure. NVIDIA Healthcare is in Azure. And all of it is deeply integrated and deeply connected with Microsoft Fabric. The whole industry is gearing up for Blackwell. This is what I'm about to show you. Most of the scenes that you've seen so far of Blackwell are the full fidelity design of Blackwell. Everything in our company has a digital twin. And in fact, this digital twin idea is really spreading, and it helps companies build very complicated things perfectly the first time. And what could be more exciting than creating a digital twin to build a computer that was built in a digital twin? And so let me show you what Wistron's doing.